Hi, this is Sam, and I'm here to present to you on Archimedes and his conoids, his spheroids, and spirals. Just a little bit of background on Archimedes. I know he is being presented on um, his life more so in background in a different presentation. But just a few facts that I thought were interesting or necessary was that he lived in Italy and studied with Euclid's successors. So he is a big math guy and other, discoveries and a thinker. And so he put together 9 treatises or 9 different works, two of which are on conoids and spheroids, and another one on spirals. So there are 2 different works that I am presenting on in this presentation. His common proof was using reductio ad absurdum, which we know as proof by contradiction, and also by proof of exhaustion. So he went through all of the possibilities for a given thing to prove, and since he proved that all of those things can happen, the one thing that he was trying to prove must be able to happen. So he was really known for proving things like that, and we will see that in my proof outline of a proof that I'm going to do for a few of his propositions. His work was put to use by designing a catapult, pulley, and burning mirrors during the Second Punic War, which is known as the Hannibalic War as well. I thought this was just kind of intriguing. It's when the Romans seized Syracuse and they in Italy, and they were afraid of the weaponry that they had. They didn't expect them to have this kind of a thing, and so they were actually kind of afraid by that. He was actually killed during this war, Archimedes was, but there is some discrepancy and rumor on about how he died. I couldn't find an exact reason or way, but all of the things that I found were either that he had some sort of mathematical motive or some sort of mathematical instruments that caused the Romans to be angry. Either he refused to go with them because he was working on some sort of mathematical project, or they thought his instruments were weaponry. Anyway, it caused the Romans to be angry, whatever he did, and they executed him during this war. Um, I think that's just kind of an interesting tidbit to know that there's some rumor out there that he had some sort of mathematical reason for why he died. So let's just get right into his On Conoids and Spheroids book. He formed a lot of ideas in this book about determining volumes of segments formed around a conic around an axis. So I think hyperbola, parabolas, but they're in 3D, so paraboloids and hyperboloids. Um, Also, something to connect it back to in your Calc 1 class, whenever we would do volumes of revolution, that was kind of the similar thing that he was doing, and integration. So he was finding the areas within these conoids um, and discovering different properties that you could use with them. He goes on to define a right-angled conoid, which we know as a paraboloid, an obtuse-angled conoid, oblong spheroid, flat spheroid, segments of cones, and frustrones of cylinders as well. And so he just goes on to define those things to set up what he is talking about in his work here. He has 32 different propositions in this book, which you can easily find online, and go and look up what these propositions are. And then here's an example in case you just didn't know, that's of a paraboloid from GeoGebra. So it is a 3D figure, and it can be filled in a sense of a volume in that way. And so I'm going to go ahead and prove 2 of his propositions that he puts together in his book. On conoids and spheroids, and he does use his previous propositions to prove this. This is only kind of like an outline of it. I didn't want to get into the nitty-gritty, but just like how you would understand him constructing this proof is kind of intriguing. Basically, he said that the volume of the paraboloid is half that of the cylinder that's inside of it, which is kind of interesting. So first he starts off by taking a cross section of the paraboloid. So he's now looking at a parabola. He slices it in half, which is what we see here is two cross sections of this parabola. He takes an under approximation and an over approximation of the volume of the curve using rectangles, which in the 3D volume sense would be disks. So he takes disks and fills it up, does an over approximation and an under approximation. So he then says that the height of each disk needs to be the same, so they're evenly heighted disks, obviously with different volumes. But he is like, okay, well, under the curve, for the under approximation, we have n-1 disks, but for the over approximation, we have n disks. So there is one more disk of bigger volume in the over approximation. But because of the properties of a parabola, he realized that the area of the first disk and the under approximation I1 is the same area as the first disk in the over approximation. And you can actually match up these areas. So I2 is the same area as C2, et cetera, and we can keep going until we realize that the over approximation has more disks. If we subtract the two approximations, we are left with the volume of the disk Cn, and that's our last volume. He makes a note that for a large number of disks, and smaller heights of them, which would make sense for a larger number of disks, our last disk becomes very small. So the error of our approximation decreases the more disks that we add, which makes sense if we think about normal integration, and we usually take rectangles under a curve, correct? And if we have more rectangles, the closer the areas of the rectangles will be added up to the area underneath the curve. So that's what he makes a note there about that. So what ends up happening is that for the under approximation, when the cylinder inscribed in the paraboloid is divided by the number of disk pieces and the volume of the disk pieces, the volume of that cylinder is twice the sum volume of pieces, so it's greater than that volume. And for the over approximation, the cylinder inscribed is when it's divided by the disk pieces, the volume is less than twice the summed volume of the pieces, which makes sense. A cylinder inside of this, the under approximation is going to have greater volume than the cylinder, than the disks inside, and same with this, it's going to be less than the over approximation, and that makes sense. And so thus, the volume of the paraboloid, when you set that inequality and divide by 2, half the volume of the paraboloid is in between those two approximations. And so now here's where his contradiction and exhaustion part comes in this proof. So he's like, okay, well, let's suppose that the volume is less, that the half the volume is less than the under approximation, and let's suppose that half the volume of the paraboloid is greater than the over approximation. He basically said in either case, I can choose enough disks that our approximations would contradict those two inequalities. And so that the volume of the paraboloid is half that of the cylinder in enclosed medium, which is pretty cool, I think, that he was able to find that volume of that cylinder inside a 3D section like that. And so that's what he does in those two propositions of conoids and spheroids. Now into his work on spirals. Sorry for the hypnotic spiral picture there, but I think it's pretty cool that showing the rotations of this spiral. Basically, he created it by sliding a point along a straight line while simultaneously rotating that line. So if I'm like patting my head, rubbing my stomach at the same time, he is taking a point, sliding it across the line, but also turning that line around a circle. And so kind of just to illustrate that here, we can see that from the origin in my green dot, the radius is increasing. If you imagine lines coming out from the zero, my point is sliding further along while also going along a circle. This spiral does have polar equation r equals a theta, so it's just a scalar multiple of whatever angle we're at. He used the spiral to make calculations of areas and circumference of circles, just because it is rotation and he has points along rotation, he was able to further describe these areas. And so one thing he did that he's known for is determining the area of one revolution of his spiral circle, which was pretty cool. But he more specifically, he taught us how to square the circle and trisect an angle. And so we're going to go ahead and just go through his constructions for squaring the circle and trisecting an angle. On squaring the circle, what he did was he let point P be on the spiral after one rotation. So he has his rotation, his spiral, the red here, and he marks a point P. And this has origin O of the spiral. He let this tangent to the spiral, it passes through P, and he let that line intersect OT at T, the y-axis at T. It turns out from his previous works that OT is thus the length of the circumference of the circle O, and so the area of O is the same area as the triangle OPT right here. And since we can double the area of the triangle to get, or we can turn a triangle into a square, he said, so we can also double the area of the circle to get a square and square the circle, which is somewhat seemingly simple, but he does take a lot of proofs to get there. And so that's pretty cool, I think. And then lastly, on his trisecting an angle, we learned a different way to trisect an angle, but his is relatively simple with his spiral. So he said, okay, I have angle ABC. We find out where this angle, the segment BC intersects his spiral, and we chop that up into thirds. And so he said BD is, and so he says BD is 1/3 of this whole segment BC. He draws a circle with the center at the center of his spiral, and he makes the radius the 1/3 of that segment. So he makes the radius BD. He considers the point E where his circle B intersects the spiral again, and it wouldn't intersect at C because it's bigger than 1/3 of the segment, and so it would intersect in another point E. Then he said, okay, so then ABE, angle ABE is 1/3 of the angle ABC. Relatively simple construction, pretty neat, all of the math workings that goes on behind this. Archimedes is known for a lot of things, as you can see in multiple presentations, but these are just two of his works that involve areas and other cross sections of things. So that's pretty cool. And then here is my works cited.